Here we're going to consider how to use dimensional analysis, basically fence posting, how we can use that to make a prediction that we can test experimentally. The way we're going to do that is we're going to consider how long it takes sand, or the rate at which sand flows out of a funnel. And what we're going to do is fill this funnel here with sand. On the bottom right here, there's going to be a hole, and we're going to measure the rate in kilograms per second that the sand flows out on. And we want to figure out what quantities will this depend upon. I want you to look at the diagram and figure out what things, measurable quantities, do you think the rate at which the sand flows out will depend upon. A little box will appear on the side, and what I want you to do is write down the quantities and the units for these quantities in that little box. After you've done that, we'll go over what the typical suggestions for quantities that the rate will depend on. Remember, the rate is measured in kilograms per second. Okay, let's consider some of the suggestions people usually do make in terms of what quantities the rate will depend upon. Most people will pick up on the size of the hole. The bigger the hole, the faster it will, the sand will go out, and the smaller the hole, the slower. And by the size of the hole, we will use the diameter, we'll call that D, and we'll measure it in meters. Another thing that people often will guess is the density of the sand, because that will determine essentially the mass of the sand that comes out. We're going to use the Greek letter rho as a standard symbol for density, and density will be measured in kilograms per cubic meter. Another thing that you have to consider is, although we're not going to change it, the only reason the sand flows down is because of gravity. So gravity certainly will affect the rate at which the sand flows out. And by gravity, we really mean the acceleration due to gravity, the little g, and of course that's measured in meters per second squared. Now, another quantity that people often guess will have an effect is the height of the sand. The height of the sand, for example, above the bottom right here. That's actually a pretty good guess, but as we see when we actually take data, that it doesn't affect it. The height of the sand will turn out not to affect the rate at which the sand flows out. We will see that because we're going to measure the mass of the sand as, in fact, it is collected in a bucket on the bottom. We're going to put a scale underneath this and record the masses as a function of time as the sand comes out. And then the slope of that line will be the rate. And we'll discover that the rate will in fact be very constant and will not change as the sand comes down, the height of the sand comes down on the funnel. So therefore, while that's a good guess, turns out the height of the sand does not matter. Another thing you might guess is the volume or the mass of the sand. Well, that actually is straightly dependent upon the height of the sand, because the shape will be fixed. The height, therefore, will determine the volume, and the volume plus the density, which we've already included, will determine the mass. So the volume is dependent on the height, the mass is dependent on the density. We've already discounted one and included the other. So it turns out volume of the sand is not important. Neither is the mass of the sand. Another thing you would guess is the angle of the funnel. How steep is this angle right here? Now, that probably does have an effect. However, the angle will probably affect the results by some sort of a trig function. We'll probably see it'll be the cosine of the angle or the tangent of the angle. And we're going to try to use dimensions in order to guess the relationship. If a quantity does not have dimensions, we can't use it in our analysis. Therefore, while this is certainly something that does affect the rate, we cannot include that in our analysis because the angle will not include any units. So while this may well be true, it doesn't help us. Other things people occasionally toss out is the size of the sand granules. Well, that probably does have an effect, and certainly in an extreme it does. If the sand granules were rather large and had a diameter of, say, an inch, and the hole had a diameter of, say, an inch, then obviously the sand's not going to flow out very fast. To compensate for that, what I'm actually going to do before we do the experiment is I'm going to put all the sand through a very fine sieve and therefore get rid of all the large pieces in the sand. So the sand will be very fine. So we'll take the size of the sand to be very small compared to the size of the hole, although we should be mindful that in the extreme case, that certainly can have an effect. We will take steps to try to minimize this effect. Therefore, the three quantities we really need to worry about are the size of the hole, density of the sand, and gravity. So, with that given, we're going to use dimensional analysis, or the units, to predict how the rate r in kilograms per second will depend on the diameter, the density, and gravity. The way we're going to do that is by assuming a certain shape for the equation. Namely, we're going to assume all of these will simply be power relationships, or the rate will equal some constant, and this will be a dimensionless constant, so all of the dimensions will be in the diameter, the density, and g. And it'll be c times the diameter raised to some unknown power, times the density raised to some unknown power, times g raised to some unknown power. And what we're going to use is the fact that the units on this side of the equation, kilograms per second, have to equal the units on this side of the equation, which include meters, kilograms per meter cubed, and meters per second squared. All of those units, when combined, have to simplify down to just kilograms per second. So the units on either side of the equation do have to match. So we can take the units one at a time. On the equation, what we have are kilograms per second must equal meters raised to the a power times kilograms per meters cubed raised to the b power times meters per second squared raised to the c power. So let's take the kilograms, and realizing that when we multiply these quantities together, we're actually adding the exponents. Remember, we're adding exponents when we multiply. So to match these, the exponent for the kilograms on this side is 1. So all of these must basically add up to 1. Well, over here, there is no kilograms, so this is kilograms raised to the 0 power, so that's 0 times a. Plus, over here I have kilograms raised to the first power times b. Here I have no kilograms again, so that's 0 times c. All of those have to add up to 1, or b must be 1. The only way to match the kilograms on either side of this equation is if density is raised to the first power. So the rate must be linearly dependent upon the density. We also have to match the seconds, so I need per seconds on one side, which means I need a raised to the times 0 to get the first term. Then again I have b times 0 for the second term. And here I have seconds raised to the minus 2 power times c, or this tells me, solving this equation right here, that c must be 1/2. Or the only way to balance units on either side of this equation, so I get just per seconds over here, is if I take the square root of g, because g is the only quantity that has seconds in it. Now, that's all fine and good, but notice I still have all these meters. All of those meters must cancel out, so I don't have any meters left when I do all the multiplication. So canceling out means the exponent must be 0. So that means basically a minus 3b plus c must be 0. Solve that equation, and that tells me that a must be 2.5. Now, we can put all of this together and get a prediction, namely that the rate the sand flows out will equal some dimensionless constant times the diameter of the hole raised to the 2.5 power times the density of the sand times the square root of gravity. Now, when you look at this right here shouldn't be too surprising that the power is close to 2. What I want you to do is think about for a moment and then answer a question. Why might we sort of expect that it might be d squared? So answer that question over on the side, then we'll go on. Now, you might guess it'd be d squared because that would give me the area of the hole. Now the hole is going to be circular. I drilled them literally with a drill. So the area would be pi r squared, or in terms of diameter, it would be 1/4 pi d squared. and you might guess the rate would depend on the area. But if it did depend on the area, the units wouldn't match. So if these are the three main quantities that the rate depends upon, it cannot be diameter raised to the 2 power. It's got to be the 2.5 power. So in effect, dimensional analysis has given us a surprising and testable prediction. So what we're going to do with our experiment is we're going to keep everything constant except for the diameter of the hole. Namely, we're not going to change gravity. I don't know how to change it anyway. We're going to use the same sand, so the density of the sand will stay constant, which means the rate the sand flows out will be proportional to d to the 2.5 power, or the rate will equal some constant, and k, the constant, will basically be everything that we're keeping constant, which is the c, the density, and gravity. And then we have d to the 2.5 power. Well, the way we're going to deal with this equation is we're going to take the natural logarithm of both sides of the equation. The natural logarithm of r equals the natural logarithm of k times d to the 3/2 power. Simplify this out with our rules for dealing with logarithms. So the logarithm of the product is the sum. And then when I use a power, it becomes the product. So that means I'll end up with the logarithm of k plus 2.5 times the logarithm of d. So our prediction is going to be that if we graph the rate at which the sand flows out as a logarithm on the y-axis, the diameter of the hole as a logarithm on the x-axis, we should get a straight line with a slope of 2.5 and an intercept that'll be the logarithm of this constant k. Key thing is we're predicting the slope will be 2.5. Now, this is what I want you to do. Noting that Excel has another way to do it. This is quite literally what Excel does, is they have what's called a power curve fit. We can do that as well, where it will calculate the exponent that best matches the data. And it literally does it by doing this analysis. I want you to literally do this analysis by graphing the logarithm of r on one axis and the logarithm of d on the other axis, and then use linear regression to get the slope. And we now have a testable prediction that the slope will be 2.5, even though our gut might tell us that 2 sounds like a more reasonable answer. So that's what we're going to test.